It's off again. Man. No, it's on. You hear me? Great. Okay. So this is my talk. I'll be talking a little bit about game design before we get into actually coding games, because it does make coding games a lot easier if you think about the design and know a little bit about the design, because it is different. My background. So as the developer, I'm a Python developer for Cox Media Group. Next to my mouth. I'm sorry, I've been screwing with this thing. How's this? Is this better, some people? Okay. I'm a Python developer for Cox Media Group. I'm a recovering beta tester. Back when I was super poor and couldn't afford to buy games, I signed up for every beta testing of games because they'll release it as a beta. And so you get the game for free. You get a really buggy game for free. And so I did this all the time. I'm not doing this anymore. It was such a headache. And I'm a beginning pygame developer. Not on actual pygame, but using pygame. And I actually have a series of blog posts as I explore learning about pygame and trying to make a roguelike. Now, my background as a geek. I've been a gamer since forever, since I was 3 years old and playing Strawberry Shortcake on the Atari. I've had a controller in my hand. I am ardently multi-platform. I do PC gaming, I've done PlayStation, I own an Xbox, I have a DS, I've had a PSP, I've gamed on the Android, iPhone, everything. I don't subscribe to just one platform. I game with my family. I have 2 kids, and I love teaching them how to game and gaming with them. We love Minecraft. We play that together. We'll play, Mario games together, all that stuff. And my biggest geek cred is I once broke up with a guy over Final Fantasy VII. So that's like my geek badge. Yeah, and I will tell that story over lunch to anybody who's interested. So why would you want to make games? Learning how to write games actually makes you a better developer. You have to be much more detail-oriented, you have to plan better, and you have to learn to throw away your code faster. Because it's a very different field than making things like web apps, which is what I was doing before I did this. I did web apps and scripts. They're really great for outreach. If you want to get a message out, games are a much better way to go viral. If you actually publish it, if you want to get people to know about your company or your cause, it can get people to a deeper understanding. It has a very immersive message. Even if all you want to do is scare the crap out of people, it's a lot easier to do that in a game than it is to do in a book. I am much more frightened of scary games than I am of scary books. I laugh at scary movies. I'll throw controllers across the room for certain games. I cannot play them. And it's a lot of fun to make games. Even when you have lots of bugs, even when you have all these issues, it can be an incredible amount of dorky fun to do this. So what is a game? This is actually a really interesting time to ask this, because the media has been asking this again. A game was released recently called Dear Esther. And Dear Esther brought up this question again. So who thinks a game is fun? You can raise your hands. Well, think about things like Escape from Darfur and Dear Esther. These were not fun games, but they were games. They had messages. From Escape from Darfur, you had to get out to the water well and see how far you could get before you died. And you played as different people in Darfur. It was not a fun game, but a lot of people played it. Millions of people played it. It was published in the media, and it definitely had game-like elements. Is it visual? Hands. Hands for yes. Well, that's a maybe, but there are text adventures that are not visual. Blind people play them. And they are still alive. There's actually a yearly competition to make games purely out of text, where it's like an interactive story. How about interactive? Our games and people are getting more wary now. Okay, interactive. Interactive is a fair bet. But what about menus on websites? Those are interactive sometimes if they're Flash-based. Are they games? No. The best way I've ever had games described to me as they're objective machines. You play a game, it gives you an objective. You accomplish the objective, it gives you a new objective, or it rewards you. And it just keeps doing this over and over and over again. So how is game design different from, say, developing web apps, from developing, standalone Python applications? Tiny decisions affect so much. I decided that I wanted to animate a character in mine. He was jumping, and I wanted him to move smoothly. And when I moved him smoothly, the entire interface to the game felt different. I realized I had to completely rethink every single flipping element I had in the game because of that one tiny decision. Resources are king. I have to work really hard if I want to crater a web app or have it crater your machine. I have to Google to figure out how to break your machine through Chrome. But I made a very simple Python app and then left it up all night and came down or very simple game, came down and I'd cratered my machine. And I had to just reboot because I had not thought about the bounds. Nuances. My favorite quote about games, this game reviewer was reviewing two first-person shooters. And he said, the games felt clunky, the guns felt clunky in this game when you compared them to this game. My reaction was, how? You're pressing the same button to shoot it. You press the shoulder to reload, and you press this to switch out weapons. How is it clunky? But it was very subtle decisions. How quickly the hands moved, the sound of the gun, the timing. It was just very subtle, tiny things that made somebody go, they felt clunky. And it is more than code, not to scare anybody, but you start thinking about things like physics and art and music, and you think a lot more about math because there's something called acceleration. If you're moving on a plane and you're moving north, south, east, and west, and then you start to go diagonal, there's diagonal acceleration. And all of a sudden you're getting somewhere a lot faster just because you chose to move northeast. And you have to consider that. You don't have that's Mike. You don't have to think about anything like this, but you might find yourself thinking about them. And it really can be very cool when you start thinking about sound effects and music. I might. Here, let me turn this one off. Sorry, everybody. This one is it keeps falling off my ear. Is this good? How do I turn it on? Hello? It was on earlier. Hello?
Try again. Keep talking.
Hello? Oh, you can hear me now. Okay, great. So the elements of a game. I have pulled up so many lists of what is a game. Some of them have been hundreds of items long. Some of them have been 5. But 3 core things keep popping up. I/O is input-output. How do you communicate with the player? The world is just all the kind of artsy, the nuances, the emotive elements, and the mechanics. How is the game actually played? These are the 3 things, those big bubbles, are things you cannot ignore. You have to consider them. You have to think about them consciously. So, world. Just where the heck are we and why are we here? These are the places where you get the emotional reactions from people. It's the things like the art, the music, the ambient sounds, the lore, the plot, the voice acting, all of those things that are just kind of the visual and auditory elements of the game. So a creepy game. Your ambient noise might be children laughing and wind and creaks. The background, see and hear, it's really not showing up very well. See, it's very dark. A lot of creepy games will actually have you adjust your set so you can see. But the background is heavy shadows and mist and bloody splatters on the wall. You might find letters from survivors that are around. That's not vital to the game, but they build an atmosphere around them. The music's in minor keys. The narrator, you might hear a really creepy narrator or just the heavy breathing of the protagonist when they're scared. The plot, you might be escaping from the insane asylum. You might be looking for the survivors of some horrific supernatural event. Compare that with a game for children, an E7 game, which is basically, it's for everyone, but pretty much if they're 7 and under, that's the only people that are going to enjoy it. Ambient noise might be children laughing. This is a great multi-purpose sound. Backgrounds, they're very bright. All the colors are very bright. The lore is cheery. Might come through narration instead of text because you're doing this for children and they can't read. The music is in major keys. The voice acting, they're very emotive voices, but they're not deep, so it's kind of a happy, cheerful thing. And the plot, find where Dora's treasure is. Input and output. How do I play this thing? How does the person interact with the game? How is this different than a movie? And how do they know they're winning? This is EVE Online, which really doesn't show up either. I'll post the slide set later so you can see it, or you can search for EVE Online. There's literally like a dozen screens on this thing. Like one has chat, one has, an auction. There's all these screens. It's highly customizable. You can move the screens, you can filter them. I don't think it's going to show up. Everything can be shown or nothing. If you right click, there's like all this contextual navigation. You can sell things, drop them, see how much they're worth on the market, that kind of stuff. Compare that with a horror game. This is a screenshot from a game. This is the entire game. There is nothing to take you out of the horrible, terrifying experience that you're in right now. There's no health bar. You don't know how badly hurt you are. You have to guess. Or you go to another screen, but that pauses the game and there's lag when you get back. So to check, you have to risk dying. You don't have an inventory up there. You have no idea what you have. You have to keep it in your head. There's not even a map. So when the nasty dog creature comes after you, you just have to run and hope you remember where the safe place is. Mechanics. Just how strong is this bomb? This is the world physics. These are things like combat. Can you play with friends? What level am I and what does that even mean? So why isn't this worth world? I get this a lot. That's because the world is themes. Mechanics don't have themes. I can take the Half-Life engine and I can make the best My Little Pony sim ever. Or I can make a horror game, or a comedy, or I can make a harrowing story about love and loss. Actually, everything but the My Little Pony game has been made with the Half-Life engine. So they've made very diversive games, but the mechanics were the same for each one. So this is Minecraft. Mechanics are key in Minecraft. Actually, this is the one where they picked one thing and they rocked it. Everything else was secondary to the mechanics of this. There's not that much music. There's few ambient sounds. There's really only the rain sound and water sound are the ambient sounds. And the mechanics are you pick up a block and you put down a block. And you can build fantastic things. You can craft things. But it was just mechanics. Everything else was just kind of put in there. They did it as they had to. Braid is another one where mechanics were key. There was one thing they added to Braid. You can reverse any action. If you press the shoulder button, you go backwards in time, and it reverses all your actions. They played with it in the lore. They talked about why you could do this, and they played with it as the game progressed. But it really was that one mechanic made it a really cool game. It made it a new game. So let's talk about tropes for a little bit. Tropes are kind of like genres, but they're way more specific, and they're super picky. A trope is a pattern. It's not a cliche. I had a lot of people tell me, well, a trope's just a cliche. It's different. It's a pattern. People expect it. New game developers will come to me, and they're going, I'm going to make the next new thing. It's going to be so awesome and so great, and it's going to be incredibly new. I'm breaking all the rules. No, it is not going to be an awesome game. It's going to suck. Your people are going to hate you for doing this, because when they play a game, they expect rules. You can break a few of them, but they expect these rules to be there. Who here likes totally experimental films or books? See two smartasses in the back, and that's it. So some examples. Here's some quick examples of what tropes are. They include things like interface, elements. They include genres. They include character types, monsters, everything. Tropes can be either really grand or really, really specific. They outline where you can suspend disbelief and where you really need to play by reality's rules. So why would you use tropes? They sound really boring. These are the grammar of games. Once the game is loaded, you can't talk to the player anymore. You're gone. So you need to communicate with that person I want you to do this. Please go get the treasure. How do you do that besides say, go get the treasure? Well, you put them in the middle of the forest and you give them a path. We know to walk down the path. Then you'll see this a lot in like Zelda games. You put them in the middle of this beautiful forest, but there's a path going that way. Well, guess I better go that way, and you go that way. We're okay with that. We're surprisingly fine with following paths. We expect it. I hate being dropped into games where there's no path. This isn't fun. I now have to construct like a very methodical search. That's not fun. They help grab attention. There are tropes to grab attention. We expect, this person is important. I made them slightly prettier. I made their clothes nicer. Go talk to them. This thing I described better. Pay attention to this. This is important. It is a plot piece. Please don't disregard this. I put a question mark over their head. Go talk to them already. It's also a ready-made structure. For, when you start making a game and you're like, well, I want to make a platformer, you can actually look up the tropes for the rules for platformers. You now have requirements. You now know how to build it. You don't have to think about some of the elements. And you can also look very carefully and go, I don't want to do that. I want to do something different. Cool, I'm going to do something different there. The rest of these things I don't have to worry about anymore. I can just code to them. They're also great for idea generation. I am hopelessly addicted to tvtropes.org. I read it like every night, and it has been a great source of ideas. When I've gone down and looked at like different games and different game types, and that'd be really cool to make. Here's a bunch of examples. Here's what people have done. It gives me a lot of ideas when I decide I want to do something. Inverting tropes. You can actually break the rules. It's okay. You can't ignore them, but you can break them. You just have to do it really well. Some examples. Dear Esther was a game that came out recently. I highly recommend it, but it's a first-person shooter with no guns. You just walk around and get pieces of dialogue. Final Fantasy VII. Who here has not played Final Fantasy VII? I'm going to ruin it for you. So basically, there's this character, she's cute, she goes along with you named Aerith or Eris, depending on who you talk to, and she's like love interest and all that. Normally when somebody's in your party, they're immortal. They're never going to die. Yet she totally gets killed in like disc 2, I think. And this was a shock. They do this more now, but this was a shock back in the 90s. We were just stunned, and they're going, oh! This is the most horrible thing ever, but it was done so well. It was a great scene. They focused on it. They didn't just kind of go, oh, well, she's dead, bye. It was a big old scene. Metal Gear, one of the Metal Gear games. Normally, if you give somebody an interface, it is reliable. It tells you how many hit points it is, how many bullets you have. Everything is reliable. The map is reliable. At some point, they have you go crazy. And you don't know how many hit points you have, and you don't know how many bullets you have, or what you're shooting, or who you're shooting. It's a very weird, mind-bending experience. But it was done on purpose. Let's talk about players not annoying them through the use of tropes. Because some things have fallen out of favor. The live system. Everyone's played Mario probably, or things that have where you have 4 lives. That's really gone out of favor. You rarely see that these days. Even Mario, like the modern Mario games, in theory have a live system, and when you run out of lives, they give you 5 more. And it's like, well, okay, I'll take them. Cool. I have no idea why they do that, but it's, that's fallen out of favor because it was basically used to eat quarters in, video arcades. QuickTime events, or as Yahtzee, my favorite game reviewer, says, press X to not die. This is when they have this really cool scene, you have to press X at the right times so that you live. And this is the most boring thing ever. Don't do this. We're trying to get modern developers to stop doing it, and you will occasionally see it in games, and those games usually crater, or they are just not reviewed favorably at all. Save points. Used to be you'd walk along and you'd come across a save point. You can save right now. And if you forgot to, you would lose hours of effort. These days, saving is much more fluid. The game knows you're about to get into some really serious stuff, so it just kind of saves in the background. And you go and you do the serious stuff, you die, because you didn't know it was coming. It surprises you. And then it kicks you back very reasonably to just a few minutes ago right before the bad stuff happened. So you have a chance to prepare and think about it and what you're going to do. So you don't lose hours just because you didn't hit the flippin' save point. Unconfigurable controls. This is a big thing. A game came out recently where you could not configure the controls, and it got blasted. It was a good game, otherwise great writing, great graphics, but they decided they weren't going to let you configure the controls. And this really hurt a segment of the disabled population called people that write with their left hand, because you had to use the arrow keys. And left-handed people like to use WSAD because it's on the left side of the keyboard. People that use their left hand could not play the game, very well. And it was a twitchy game. So it cratered because, 15% of the population is left-handed or something? We had issues with the game. So let's talk about audiences. You have 4 kinds of people that play games. And the first time I saw this, I'm like, I don't like those names at all. This is Bartley, by the way. I don't like those names, but the more I actually looked at them, the more they made sense. So on the axis, you have what people like to do. They either like to act or interact. They like to interact with something or they want to do something. You have players in the world, things they're going to be interacting with. And you have the 4 categories of people: killers, achievers, socializers, and explorers. And people can be more than one, or they can be a combination, or they can change depending on the game. Because when you put somebody in a game where you tell them, I need you to be this kind of player, and they're okay with that, you can't switch down the road and tell them, well, now you kind of have to be another kind of player because I've changed the game. Even if they like being that other kind of player, it can really cheese off people because it kind of breaks with their momentum and their thought processes. So let's talk about explorers. Explorers like interacting with the world. These are the people that will do every side quest. They love side quests. They will actually ignore the main quest in Skyrim and Fallout and all that, and they'll do all the side quests before they even bother with the main quest because they want to collect everything. They want to collect all the guns. They want to collect all of the kinds of, rat meat and drinks and beer and stuff like that. They want to talk to all the NPCs and get all the cool dialogues. If you want to make these people happy, give them stuff to explore. Give them a world. But put care into it. Make sure you have lots of items in that world, that you describe everything well, and you give them a rich environment to play with, and you don't put them on rails. Rails are when you basically say, well, you're at event A, and now you have to go to event B. Go. Okay, now you're at B, go to C. Go. And you don't give them a chance to diverge or do anything different. Achievers. Achievers want to win. I will admit it. I am usually an achiever. I want to win the stupid game, and I want to do it without dying a million times. Give them stuff like badges or satisfying endings. If I've spent 40 hours on your stupid game, it had better be a really good ending. I had better have felt that my time was well spent trying to get to this ending. If you want to frustrate them, kill them over and over and over again. Or put them in a place where they all of a sudden cannot win. Which I've been in. I was in a game where I was stuck in a room, couldn't go back, couldn't go forward, was out of health potions, was low on life, had nothing to help me, and basically I was told, well, I guess you'll have to go back, a couple save points. And I'm like, no, I want to be able to walk out and leave and collect what I need and then come back and kill the thing. But it was impossible, and my last save point that I had backed up was literally like 3 days before that. So hours and hours and hours of work. Killers. This rose has another name, griefer. These are the people that get into games, especially social games, to screw with people. They like to act upon players. If you want to make these people happy, put in PvP. Give them rewarding PvP where they can actually get badges and stuff and get experience and get their stuff. EVE Online is a game that's basically made for economists and griefers. Because you're in spaceships and you can blow each other up. No problem. You can blow each other up, and it's an excellent game. I mean, they made it for these people. It's no accident. If you want to stifle these people in your game and you're making an interactive game, because these people mostly will be in games where it's interactive, where there's a world of people. You would want to do quick bans on people that do it. You want to take out PvP. Understand that they'll find other ways to grief people, but you act on their actions very quickly. So if you want to control these people, you need to think about how you're going to control them and make them unhappy and make them go away. You can't make them play by the rules. They will find ways around it, but you can make them unhappy. Or, make a game for them and make lots of money, like, CCP. Social is our last category. Social is actually the largest group. And some people go, oh, it's the MMOs, oh, it's the stupid Facebook games. But games are social. Games have been social since we've been, rolling dice and playing Mancala when the pyramids were being built. It's always been more people. It's only been a very small blip in history that games have not been social. It's been very few, like maybe solitaire or a few things, or puzzles. But for the most part, they've always been very social. And we're now returning to that social element of games. Yes? 5? Okay. We're just going to skip ahead really fast. Okay, I'm sorry. A word on the war of the sexes. The numbers fluctuate, but women make up about half of gamers. This has not been what people they've always assumed all gamers are men, and there's like a few weird women in there. It's about 50-50. The last numbers I heard were 53. 53% were female. And they're not just playing Diner Dash, okay? I know plenty of Halo players that are female. I know women that play, Fallout. I love, freaky horror games. And when polled, they've done a lot of polls trying to figure out what women want in games. And while women sometimes complain about the proportions, the unrealistic proportions, one trope made them angrier than anything else. And that was something called the woman in the refrigerator. Who's familiar with it? Basically what happens is women are only brought into a game when we're going to kill them and the male character is going to have to go avenge them, or they need to be kidnapped and the male character needs to go rescue them. And that otherwise the woman either doesn't try to defend herself from being killed or escape from the captors. And it actually comes from comics where they literally did put a woman in a refrigerator twice. They didn't learn their lesson the first time. And so if you want to attract female gamers, try not to do this. You don't have to make Bayonetta, make this kick-ass woman, but either just try not to make women like these things that you have to, capture, or recapture or avenge. Do something else with them. So genres, hands up, all hands up. Put your hands up. Okay, so put your hand down if you have not played the following genre in the past 2 years. Okay? Role-playing game, MMO, casual, JRPG, action adventure. We have more geeks in this room than I thought. Normally a lot of hands are down by now. I'm trying to think of one more. Puzzle, platformer. Hey, you had 2 hands up. Put your other hand down. So, yeah. I'm down to 2 people in this room, or 3, by the end of this. And the rule and basically this is you need to play more games. Because you have to understand all the genres. And I understand some of them suck, but you don't have to put that much time into them. You can also mix genres, which is kind of cool. People are doing this more now. Just don't go too crazy. I hate it when it's it is a rhythm platformer RPG with social elements. That, try to stick to 2 genres. So how do you get more exposure to genres? Because there are certainly things I can't play. They're too scary, they're too hard. You can cheat. YouTube to the rescue. I watch a lot of Let's Plays of games that I either physically cannot play because I have a hurt hand. I can't do Guitar Hero, for instance. I will go and look up Let's Plays. All you have to do is just say, let's play, yada the game, and you can watch people play the game for you. And you can even hear their frustrations, which is a really interesting exercise. Also, you can get free demos. So, how do you make an awesome game? You're going to make a lot of bad games. Just accept it now. Make bad games, throw out the code, don't try to rescue it. Once you're done, throw it out, try again. You're going to slowly get better. Every game developer I've ever talked to, the first successful game they had was usually about 10 to 15 games in. The one that they finally felt they could show their friends. So, some further reading. I'll post these up later because I'm running out of time. I ran over. I'm so sorry. But thank you all very much. And we'll just do combined questions at the end if we have time.
Yeah.
Yeah.
Who's played around with photography? Use the mic.
Oh, this is kind of off the mic. I'm just curious. Yeah, there's a few. So you know about the rule of like when you're taking photos, especially when you start out, you're 1 in 10 photos, maybe 1 in 20 photos is actually worth keeping. It's kind of like that with video games. Anyway, so let's get this. I'll give that a try. Yeah, let's see if I can get it to.
I have weird ears. It wouldn't stay on me. Hair and stuff.
Yeah, that's staying there, is it? Yeah.
Does it stand? Is it, well, it just
Well,
feels
I'll
right.
try not to jump around, but that feels like it's
That
staying.
doesn't look right
Doesn't look right? It's staying.
to me. Okay, as long as you're...
Yeah. Sure, I'll turn it on too. That'll be handy. All right. Oh, where'd the? Oh, there it is. Okay, so that was a really good introduction to the theory of what makes video games. So what we're going to do now, all things going well, is we're going to spend about 2 hours, a bit over 2 hours, actually constructing a game from scratch. And we're going to learn a few things along the way, hopefully. Oh, yes. Okay, so now I actually saw somebody yesterday with a cup of water pour it all over stuff, so that's why I'm going to be very, very careful and not do the same thing. Okay. Let's put that back. Try and keep this thing under control. That's good? That's all good. All right, so let's write a video game. I've got around 130 slides to get through. We'll see how we go. And you should all have the source code and the pygame docs on your computers now. Anyone who doesn't? Nope, all good? Excellent. Okay, so first thing, and this goes back to that last point there about, well, somewhat last point, about you have to write a lot of bad games. I'm going to be covering a whole lot of ground today. So you've got the source for a simple game there, and you're free to do whatever you want with it, okay? I'm not putting a license on it as public domain, it's whatever. It's yours to play with. So experiment with it, break it. The actual code is up in a Bitbucket repository, so if you do horribly break it, you can just grab it back again and unbreak it. And just muck around with it, because a few years ago I was just like you, I didn't know what I was doing, and I've very much learnt how to make games by, I think I've written a good couple of dozen games by now. So, and I think I'm getting a hang on it. So, yeah, write lots of games and break them. So the basics of what we're going to do today, these are kind of the core ideas of what makes a video game, or sort of like the most common video games, the basic elements of putting something up on screen and having some interaction with the user, having some rules about how the game behaves, the mechanics of the game. There might be some sound effects and some background music as well. And then I'm also going to be talking a little bit about how you some ways that you can organize your game code so that it's a little bit more manageable and sort of the architecture of the game code itself. So to jump straight into trying to get something fun up on the screen, we're going to go straight into the basics of getting something displayed on the screen. Which involves opening a window. Now, if your game is going to be a full screen game, that still requires opening a window. It's just that it's a window that covers the entire screen. We're going to then need to draw something in the screen and move it around, because games are more fun if the stuff is moving around. In terms of drawing things on the screen, we've got a number of different things we can do in pygame to achieve that. We can take an existing image, which may be loaded up off disk, and we can copy it straight onto the screen. We can use a number of tools that are available in the pygame.draw module to draw things like rectangles and lines and circles. We can draw text using the font library. Or we can skip all past all of that and we can draw things on the screen using OpenGL. I'm not going to be covering OpenGL today. This thing's wobbling away from me. Because that's a whole other ballgame. But I can certainly give you some pointers if you'd like to ask me after the tutorial. So in terms of copying images around, as I said, we can load images off disk. Pygame understands how to load JPEGs and PNGs and Targa files and Windows bitmap files and a bunch of other different formats. We can also manually construct images using array-like operations. The Pygame surf array module gives you an interface to something that works with numeric. So you can actually use math to create your image. Or you can construct, you can use the Pygame draw commands to draw into a surface that's not actually on the screen. You can draw something that can then be stamped multiple times over the screen, the same image constructed using the draw commands. So those are the various things we can use. We're going to use a few of those today. But the first thing what we're going to do is we'll open up a window. So I'll invite you now to execute the code 01 open window. Do you have the code there? You can follow along? No, okay. Okay, so you will hopefully, if it didn't crash, and if it crashed, sorry, you're out of luck, but you should have seen a window kind of flash onto the screen. The speed of the flashing kind of depends a little bit on the speed of your computer, but yeah. So this is the code that you just ran. I'm really hoping that you can read that. If you can't, I'm afraid you're going to have to move up because I can't make it bigger. So there's a few things going on here. Obviously, we're going to be importing Pygame. That's kind of at the top of all of our Pygame games. The next thing, the very first thing that you should run at the start of a Pygame game is pygame.init, because that initializes a whole bunch of the libraries inside Pygame. The things that you use to manage the screen and load images and render fonts, all those things have to be initialized before we can use them. So that should appear first, after you've imported Pygame, obviously. Then to actually open the window, we invoke set mode on the display in the display module. Now it's kind of an obscure one. It's not called open window or something because Pygame technically already has a window open as soon as it's running. It's just that it's an invisible window. And so what we're doing is we're setting the mode on that window to say set yourself to be 640 pixels wide and 480 pixels high. Sorry, this thing's wobbling away from me. I'm going to try and wrangle it in there. I might switch back to the other microphone if this gets too annoying, but we'll see how we go. Okay, so there's a whole bunch of other arguments that you can provide to set mode. I'm not going to cover them all. The simplest is just to pass it a size. Now, because there's no further code, and that returns a surface, a Pygame surface, which you can then draw things to. Because there's no further code in that program, it kind of hits the end and exits. That's why the screen just kind of flashes up. So what we need to do is introduce some more code so that our program doesn't just quit. So if you run O2 main loop, you'll see the window stays open. It doesn't do much, it's just a window. The reason why it's staying open is because we've introduced this concept of a main loop. And this is the loop of code that just keeps on running and running and running and running inside our program to keep it going. It also does things like handles events for us. So this is the most basic kind of persistent Pygame program that you could have. So, and this is the most basic form of event handling as well. Events are things that happen outside of our program and come into Pygame, and Pygame handles them and passes them off to you as useful data structures to tell you that something has happened outside of your program. So things like the close button on the window being clicked, or a key on the keyboard being pressed, or the mouse has been moved, or various events coming in from the computer or the operating system. And we can see that the event tells us what sort of event it is. So we have an explicit quit event which says the operating system has told the program to quit. Key down events are when a key has been pushed down on the keyboard. We also get key up events. And the different event types also have different properties, additional properties on them. So the key down event, or the key events, also have a key associated with them. You don't get the key with the quit event. Okay, so I'll ask you to run 03, and it should actually not change very much. Hopefully it won't change at all, actually. But what we're going to do is we're going to take our code, which looks like that, which is quite unstructured, and we're going to refactor it so that we're already starting to introduce some sensible architecture to our game. A lot of games, when you a lot of games that I certainly started writing out, they would just be like this in the top level of a file, effectively, a Python script. And it would just run, and there would be lots of globals, and it was all a bit of a mishmash. It's a really good idea to move away from this sort of program to this sort of program early on, so that things are more organised, because you'll find that getting into this habit is a really good idea as your games start getting larger. We've got code that's standalone, it's re-enterable. We can create this game and run it multiple times. It can contain its own state. We can set attributes on this game object, which we can then share with other parts of our game. We don't have any attributes yet, but we will. It's a really good place to store a reference to our player or our playing field or our enemies, bullets, everything that's kind of alive in the game. And that allows our various other bits of our code to access that information without having to resort to using global variables. The game could very well be just called level or world or whatever's appropriate for one sort of chunk of your game. Okay, so we've got a blank window up. Let's draw something to it. Because once we've drawn something to our window, we've actually achieved enough to be able to write a bunch of different games just by drawing something to the screen. To do that, we have to know a few things. First of all, where are we going to draw things onto the screen? And that involves understanding Pygame's coordinate system. The coordinate system tells us how to position things on the screen. So if you'll recall, our window is 640 pixels wide and 480 pixels high. The Pygame coordinate system is a little bit old school. Y increases down the screen. And this is kind of a historical artifact because of the way that older computers worked. Screens are refreshed from the top down, actually across and then down. And in these older style games, older computers, programs would be writing directly to the video RAM that represented what was up on screen. So it kind of just made sense for the start of the video RAM to be the top left of the screen. The refresh mechanism is obviously still the same today. Screens still refresh from the top down, but modern graphic systems like OpenGL and DirectX use a Y up coordinate system because they're divorced from the video RAM, and it just makes more sense to have Y increasing up. But Y increases down in Pygame, and that will catch you out at least once. Did you all run the 04? Yep. So this is the change to our code from the previous version to allow us to draw the image. Now, there's a few things going on. The first thing is that we've loaded an image off of disk. And it's a PNG file, but again, Pygame can support a bunch of different file formats. the nice thing about PNG is that it has an alpha transparency channel. So if our PNG has transparency in it, Pygame will understand that and it'll blend the image into whatever it's drawing onto. And so the image that we're actually drawing up, the stick figure, has transparent bits so that the background comes through where there's, the image tells it to. We clear the screen to wipe out anything that was previously there, and we use a colour grey, and I'll come back to that in a second. And then we copy the image that we've loaded onto the screen using the blit command. And again, the term blit is quite an old school term. It actually is an acronym. It stands for Block Image Transfer, which kind of describes what it does. It's copying an image, a block of an image, to the screen. And we tell it what coordinates to copy that to. And that's the top left coordinates to place the image at on the screen. And then we flip the display. And I'll come back to that in a second too. So the colour that we've drawn in the fill is specified using red, green, and blue coordinates as a 3-tuple. And the values of those components range from 0, which is dark, to 255, which is full colour. And you can pretty much get those colour values from any program. And I stole this image from Katie's blog post talking about this. Okay, now the flip thing is a bit fun. So you can draw directly to the screen if you want to. And the problem with that, though, is that screens are updated. Even your modern LCDs are updated in a serial fashion from the top down, as I mentioned before. And because the screen is being updated at the same time that you might be drawing to the screen, you'll get a varying image depending on whether the refresh is happening at the same time that you're drawing. Now, there's a couple of programs in the folder there that I would ask you not to run if you have a problem with strobing lights or anything like that, because it does flash a lot. But you can run 04-tearing. This won't work on some of your computers, but hopefully what you'll see is a bunch of flashing, but you'll also see a line across the screen, which will vary in its position. If you don't see the line, then maybe we can look at somebody else's computer. The Macs should run it fine. Yeah, it's a bit bright. So the line that you see across the screen is what's called tearing. It's representing the screen refresh update is happening while we're changing the colour of the screen. If you run 04 tearing fixed, what we're doing is we're changing the program so that we're not actually drawing to the screen as it's refreshing. We're drawing to somewhere else, and then we're copying that image that we've drawn to the screen after the screen has updated. So you should see solid changes of colour from red to blue without any tearing. And your eyes will be bleeding. You should not see the line moving up unless your OpenGL implementation is a little bit broken. Sadly, it's a bit of a rough test because it requires that vertical refresh syncing is supported, and some computers won't support that.
So on the Mac, I'm just getting a blank screen.
That's brilliant. No, you shouldn't see a blank screen. All right. And this is why we're not doing the tutorial in Piglet, by the way, which I much prefer over Pygame, because OpenGL is just notoriously bad. The support is just terrible. Anyway, so let's move on. So the solution to our tearing problem of drawing to the screen while it's being updated is to draw to somewhere else. Instead of drawing directly to the video RAM, we're going to draw to a different part of RAM, and then once we've finished drawing, we're going to tell the display system, stop drawing what's in that bit of memory and start drawing what's in this bit of memory. So we switch the screen over to start drawing the new thing that we've drawn. And then we'll take the old thing that it was drawn and we can start drawing our new screen to that. We call those buffers. And so the pygame display flip does exactly that. The flip says to pygame, start drawing to the screen this other buffer. And pygame manages the two buffers for us automatically. We don't have to worry about actually changing the buffer that we're drawing to. The screen that the object that we're using always points to the drawing buffer. And pygame by default gives you this double buffered implementation. So anyway, that's flip. Now, the reason I bring all of this up is because at some point, probably early on, you'll write a game and you'll run it and you'll be looking at a black screen and you cannot figure out why it is that you're not seeing the things you're drawing, and it's probably because you forgot to flip the screen. I did that at least once. Okay, so let's use less CPU. I'd like to invite you to run 0.5. You will probably see no difference whatsoever, hopefully. The reason is, all we did was we altered the program so that it was using less CPU on your computer. We're using a built-in facility in Pygame called the clock to limit the number of times we're running our main loop to 30 frames per second, or 30 times per second. The clock.tick call there says, does a little micro sleep, if necessary, to slow things down so that it's not called more than 30 times per second. It just sleeps if it's been less time than that since the last time it was called. Okay, so we're not hitting the CPU flat out anymore, so that's a good thing. An important point to make, though, is that if your computer is slow and it's not running as fast as 30 frames a second, it's not going to somehow artificially boost your CPU up to run at 30 frames a second. It's going to limit the speed to that. Okay, so let's do something far more interesting. Let's run 0.6 and move something around the screen. Well, across. And again, if you'd like to, open these files up in an editor while I'm talking, whatever. Have a play around, change them, whatever. So to move an image around the screen, all we have to do is alter our blitting command, our drawing command, where previously it was using a fixed coordinate, and we alter it so that it uses a couple of variable coordinates. So then inside our loop, we can alter the X position and it'll move slowly across the screen.
If you move it out, obviously, if you move it outside of the screen area, it doesn't throw an exception or anything like that.
No, it just won't be drawn, yeah. Pygame will just basically skip over that drawing because there's nothing to draw. It's out of bounds. Pygame is very much like Python itself. If you cause it to crash, then it's probably a bug in Pygame. Okay, so there's a couple of things. You could try altering the X, thing increment there. Another thing you might like trying to do is grab the fill line here and move it from here up to just before the while one. Okay, so the fill happens just before the loop starts, and run that and see what happens. And what you'll hopefully see is that screen buffer flipping in action, because we're no longer clearing the buffer after each flip. We're drawing on the old buffer. hopefully somebody at least will say, oh, look at that. Lots of little dudes across the screen. Okay, so that's basic animation. Animation 101. Awesome. Let's involve the user now. All right, I'm going to give up on this thing. It's flopping all over the place. Can I switch to the other microphone?
Yeah, you can switch.
Yeah. All right. I'd rather not have to hold it, so I'm just going to whack it here. Hopefully that's good enough. Okay, so let's involve the user. Let's get some user input. Our game is going to be primarily keyboard-based. There are other input methods that we have. We have mouse control and even joystick control. I'm not going to be going over mouse control in depth or touching on joystick control at all. There is an example game in the directory you've been given that does have mouse control, but we'll come back to that later. Events for the keyboard come in a couple of types, key down and key up, which is basically, the key has been pressed and the key has been released. Pygame sends you all of those key down and key up events. Even if the player is bashing away at the keyboard, you'll get all of them. If they have a key repeater thingy hitting the keyboard, okay, you'll get all of those key down, key up events. They can be a little tricky to manage. So there's also a global in Pygame which keeps track of the key pressed state of each of the keys on the keyboard. So you can ask, is the spacebar currently being pressed? Are the arrow keys currently being pressed? So we'll be making use of those so that we don't have to remember in our code whether or not a particular key has been held down. Pygame's going to look after that for us. The problem with the key pressed state dictionary is that you might miss some very fast impulse events. So when somebody is really quickly tapping a key. There are some events where, so for example, a spacebar to jump or another key to shoot, you might actually want to look for the key down event instead of just looking at the state dictionary. I'm going to cheat in this example and just use the state dictionary because it's a little bit simpler, but you might want to look into that. So if you'd like to run 07 user input, the arrow keys should move our little dude around the screen. And the way we do that is we replace our fixed image X position movement with a bunch of lookups into this key pressed dictionary. So the Pygame module has a whole bunch of these K constants defined in it. Obviously, these are the constants for the arrow keys. All of the letter keys and number keys are in there. So K underscore A is the A key, and so on. So just quickly, I'm just going to mention the mouse events. So we've got some keyboard event handling in our program there for the escape key. Mouse events come in basically three flavors. We've got the button presses down and up, like with keys. We've also got motion events. So every time the mouse is moved, a mouse motion event is generated. And as you can probably understand, the mouse moving, generating all these mouse motion events, that can be a lot of events. Pygame also has the ability, like the key pressed handler, you can query the mouse to ask what position the mouse is in. So you don't have to manage all of those mouse motion events if you don't want to. And there's also a global that keeps track of the state of the buttons to find out which ones are actually pressed or not. The buttons are just the values 1, 2, and 3 for left, middle, and right. There are also buttons 4 and 5, so you'll get mouse button down and up events for 4 and 5, which are the scroll buttons when the scroll wheel is scrolled. I think like 4 is up and 5 is down. All right. So that's just mouse events quickly. And as I say, there's an example, bit of code in there that uses the mouse, but we'll come back to that later. Okay, so what we're going to do now is a little bit more reorganization of our code to make things a little bit saner. We're going to use a thing called sprites. So the concept of an image and its location on screen is, a really common thing in video games. It's so common there's a name given to it from like ages ago called sprite. Sprites are an image and its position on screen. Even better, in pygame, sprites are actually defined by an image and it's the rectangle it occupies on the screen. So we actually know what space on screen it occupies. So what we're going to do is take all of the code that we used to have in our main loop, which was all a bit messy and disorganized, and we're going to place it into a nice little class, which is based off of the pygame sprite. And it's going to manage the image and the position, and it's also going to take all of that stuff we were doing to update the player on the screen, and it's going to manage that stuff as well. So everything to do with the player and the update of the player is all in the player class now, nice and neat and organized. The code itself is still, basically the same. The big difference is that instead of modifying that image X and image Y, we're modifying the X and Y position of the rectangle of the sprite. And when this sprite is drawn, it automatically looks up the image attribute and the rect attribute to figure out where and what to draw for this sprite. So now instead of just loading up our image, we create our sprite. Because games usually have a whole bunch of sprites in them, we use things called groups in pygame to manage them. So we add our sprite to a sprite group, and the group lets us do things like, in one batch draw all of the sprites, and in one batch update all of the sprites.
What is a sprite update? Is that an update to the parameters of the sprite, or or is that a movement of the sprite?
It's basically it's something that you invoke on the sprite once every run of the main loop to just update it for that run of the main loop. So it's just doing whatever it needs to do. It could be moving it around. It could be just running a timer to see if it needs to do something. It could be handling events like we are as well. The update method on our player is going to get larger as we add more stuff. One of the nice things about the group update, is that it can take arguments, and we'll use that in a little bit. Any arguments we pass to update on the group will be passed to all of the sprites that the group manages. And yeah, instead of just blitting the image manually onto the screen, we draw the group to the screen. Excuse me. Yeah. Okay. So this is just a really nice way of organising our code again. And as you can see, our main loop is keeping really tight. It's small. There's not much code in it, and that's good. You want to keep as little code as possible in your main loop. You want to delegate all of that updating code and all of the drawing code and everything to the things that actually belong to. Right. Now, you might have recalled I mentioned before that on some slower computers, our target refresh rate of 30 frames a second might not be achievable. Obviously, we've got a very, very simple game here, and if you're not running at 30 frames a second, then I pity you. But once you add lots more sprites, you will run into the position where on some computers, it won't be running at 30 frames a second. It might be running at 20 or 10. So what we can do is we can add some code to our game to handle that so that the game still runs at a constant rate, even if it's not drawing to the screen at the same rate. Okay, so if you run 0.9, nothing will change unless you're on a terribly slow computer. And what this code does is it adds a little bit adds a little bit of handling so that we're actually managing or taking into account the speed at which the program is actually running. So one of the nice things about the clock.tick is it actually returns to us the amount of time that's passed since the last time it was invoked. A little oddity of pygame is, though, that it actually returns the time in milliseconds, not actually seconds. So if we want a seconds value, we actually have to divide it by 1,000. And we divide it by a floating point value, 1,000, because the value is almost always going to be less than 1. In fact, if we're running at 30 frames a second, it's going to be 0.03 seconds. So as I said before, any value that we pass into update will be passed on to the sprites that the group is managing. So now in our sprite, we're being passed in our delta t, or change in time, dt value. And we can use that in our movement calculations. So where previously we were moving by a fixed value of 10 pixels per update, we're now moving at a fixed value, fixed speed of 300 pixels per second, which at 30 frames a second is actually 10 pixels per update. So the motion doesn't change in speed from what you saw before unless you're on a very, very slow computer. Is everyone cool with that? Yeah, I'm assuming that you'll just jump in, by the way, if you do, hands up, whatever, if you get caught out, please do. I forgot to mention that at the start. Okay, so we have this game slowly being constructed here. What we need to do is add some more stuff to it to make it more gamey. So what we're going to talk about now is making the picture on screen a little bit more interesting by constructing a scene. Scenes in video games are really easy to construct. You're just going to draw more stuff. And the stuff you draw at the back is going to be in the background, and you just keep drawing layers of images on the top of that to make up your scene. So we might have a sky, which we draw some background onto, and the background might be fixed or it might move. And then we draw some foreground images. And these are kind of like, at the where the player exists in the game. Little player. And then sometimes we might have a second foreground layer which is drawn over the top of that, so that we can have things like grass that appears in front of the player, or rocks or whatever that appears in front of the player. So we've got different layers depending on what's actually in the scene. This imagery is actually it's actually from two games. The scenery itself is from one game, and it's all drawn in Inkscape. And it was, I created it for a game I wrote for a Pi Week a few years ago. And I did all the graphics in Inkscape, and I could actually render that directly into my game, and it was really neat. And there's actually a presentation I did a couple of years ago that's online where I talk about how this scene was constructed in more detail. The little character there is from a different game that I wrote, which was a kind of a turn-based strategy game. It was kind of neat. But anyway. So scene constructing. Let's construct our game scene a little bit better. So if you run 10 now, the background one, you should hopefully see, instead of the plain background, you'll get a nice coloured background. Very exciting stuff. This is how most games evolve, though. I mean, you just slowly add bits and pieces to them, and they evolve, and they get better, or they sometimes get worse, and then you change it, and they get better. And what Katie was saying before about, every now and then you stuff up, and it just goes all horribly wrong. Sometimes that can be really inspiring. It's like, it's gone wrong, but it's kind of cool. Let's see where we can go with that. But yeah, this evolving, iterative development, this is how games, this is how you write games.
Question.
Yeah.
Holding down both opposite keys, like left and right simultaneously.
And you don't move?
No, they actually does move.
It does move.
Yeah.
They should cancel out.
It moves left.
He is probably getting in every once in a while.
Hmm.
There seems to be a bias or something. I'm just curious.
Which way is yours moving?
It might be your keyboard, it can only attack the last key pressed.
It happens to me too. Just move much more slowly.
Yeah,
than
right.
normally.
Oh, there might be a floating point thing going on there. Okay. Yes, I have to admit, I didn't completely look into the behavior of pygame when you feed it floating point coordinates to sprite positioning, so it might be that we've just got a rounding error there. Right, so what we've done now is instead of doing a fill on the screen of just a solid color, we're loading a background image up from disk, which as you can see is extremely exciting. It's just a solid fill. Sorry, it's a gradient fill. It could be anything though. I mean, you could go and you could load that PNG up and you can draw all over it and change the background image. And it's just a solid image. It's a 640 by 480 image. And we're loading it up and we're blatting it onto the screen instead of filling the screen. Yeah.
I noticed that the image can go out of bounds. Is there a way to put a boundary? Or you disappear?
So are you saying you'd like to have the drawing area be smaller than the screen, the window?
So he stops.
Oh yeah, it's completely up to your control. So we're inside your loop, where and we'll be coming back to this in a little bit. But basically, where you're updating the the X position, for example, you can just say if the X position is less than 0, don't make it less than 0, or if it's greater than 320 minus the width of the player, 32 order pixels or whatever it is, then don't move it that far. Yeah. So you just put some bounds in your code to do that. Again, though, pygame doesn't care. You can draw off screen, and it's like, yeah, whatever. I'm not going to draw anything. There's no screen there. Okay, so we've got a basic scene. We've got some user control. This is awesome. It's not a very interesting game. Let's introduce some mechanics. Okay, so the mechanics of a game involve things like how the player interacts with the game. Okay, we've got that under control. We might have some timing rules, so we'll have some timers running in the background of our game, and so things might happen, like enemies might just appear after a certain amount of time, or doors might open, or we might move the entire playing field over time. How the player interacts with things in the world, so if there's spikes, then that's got to hurt the player, or if there's a bounce pad, that's got to bounce the player, or all the various things in the game that the player might interact with. But also we have to detect, has the player killed all the enemies? Has the player been hit by a bullet and killed? All of those things. Those are all the mechanics of the game, and all the things you have to think about handling. What we're going to start off with is putting some bounds on our game so that the player can't run out of the world and can run into things. Okay, so this is interaction with the game world. So if you run 11, you should now see some walls appear around the game, and the player will be stopped by the walls. Okay, so what we've just done is introduced some basic collision detection, along with our basic mechanic of stopping the player from running outside the game. Or in fact, to enable us to stop the player running outside the game. So collision detection. Let's talk about that for a little bit. There's 4 basic approaches for detecting collisions in games like this, in like 2D games. The same concepts can be extrapolated to 3D games as well, so they're quite applicable to if you're going to be doing a 3D game. The simplest, by far, and the most common method is you take a box around the objects that you're going to test for collision, usually just defined by the image that draws the object, the dimensions of the actual image of the object, and you see whether or not those boxes overlap. And if they overlap, you've got a collision. And it's really easy to detect this sort of overlap. You look at the left and the right, and if if the right hand's bound of the ship is further right than the most bound of the asteroid, and you just check all the bounds, and if they're all overlapping, then you've got a collision. So that's really neat. Really, really simple. It's like 8 lines of code if you properly indent the condition handling. All right, so unfortunately, it can result in some false positives. So here, for example, you can see that the things are obviously not overlapping, but the collision will happen anyway. The thing is, though, in most games, it doesn't matter. In a fast-moving game, the player isn't going to notice this sort of false positive. They're like, well, yeah, I got too close to that asteroid, I should die. A slight variation, though, to give the player a little bit of more benefit of the doubt, is to just reduce the size of the box slightly. So quite often in the implementation of this sort of thing, you'll find that the bounding box will actually be, a few pixels in from the boundary of the image. But it's just easier just to use the boundary of the image. Okay, so that's our axis-aligned bounding. Oh, it's called axis-aligned bounding box because the top and the bottom are aligned with the x-axis and the left and right are aligned with the y-axis. It's not a rotated box. Rotated box collision detection, that's a whole other ballgame. Okay, so the second most common would be circle-to-circle collision. And it's basically the same as the first one. We're kind of just defining a circle that covers most of our image. And in fact, in a game like Asteroids, you would use circle-circle collision detection because it just suits the shapes better. And once we've got our circles, we then just compare the distance between the centre of the circles and see whether or not that's less than the combined radiuses of the two circles. So our previous false positive is now handled, and here's a collision. Then, of course, we'll have some missed collisions as well. But again, the player is probably not going to notice. Or if they do, they're like, yes. Whatever. Okay, so games move fast. The player is not likely to notice this sort of error. The third method of collision detection in a 2D games, and again in 3D games use this sort of method in 3 dimensions as well, is using a hash map. And the idea is that we take our various objects and we figure out which 10 by 10 cells of our game world those images touch. And so and 10 by 10 is an arbitrary number. The actual resolution of the hash map grid can be whatever suits your game. So we take each of our objects and we place a little note in a hash map to say this asteroid occupies these cells, the ship occupies these cells. And then when we want to check for collision, all we have to do is look up the cells. So, for example, the cells that the ship is occupying, we look up the cells to say, is there an asteroid in any of these cells? And if there is, we've got a collision. We can do the same thing for the bullets. This is a really good technique to use for games where there's lots and lots and lots of things that could be colliding, particularly for games like bullet hell shooter games where the player's just spewing out bullets and the enemies are spewing bullets back. You've got so many collisions to check for, you couldn't possibly check them one against the other. You'd use a hash map to chuck all of the bullets into the hash map and then see if there anything, you then resolve all of the other things to see if there's any collisions. And you do it all in just one pass. Far more optimized, but a little trickier to implement. The final collision detection method is where we compare the individual pixels of our little ship against the individual pixels of all the things that the little ship might be colliding with. And if they in fact overlap, then we have a collision. This is horrendously expensive and almost always overkill, and oddly enough, it's the first thing that a lot of people think about doing when they start writing video games. It's almost always unnecessary. Very few games actually use this method. There are some games that rely on pixel-to-pixel collision detection, and it works really well. But they'll really minimise. They'll probably do some hash map-based, culling of potential collisions first, and then they'll focus in on the actual pixels. But yeah, very, very few games need or actually use this sort of collision detection. Okay, so in terms of what our game is actually doing, we're going to be using the axis-aligned bounding box method. And so what we've done in the code is we've added some obstacles just by using a simple double loop to add some new sprites to the game. And we've added them to a new group called walls, so that we've got easy access to those new sprites for later on, for actually checking for collisions. And you can see that even though I've added all of the wall sprites to a group called walls, I've added the walls group to the existing sprites group, so that then when I can just call sprites.draw, and the sprites group says, well, there's a group here, I'll call draw in the group. And it just passes that on. So then we can draw everything. The other minor change we're going to make is that we need to get access to this walls object from inside our player update to check for collision detection. So when we invoke the update, now we're passing in the time that's passed and the game object itself. So the player update now gets a handle on the game and all the things that the game contains. So then inside our player update, we get the game object and we can use that to test for collision detection. And we're doing a really, really simple collision detection and resolution here. The detection is handled by pygame itself using a thing called sprite collide. Sprite collide takes a sprite, a group of other sprites, and tests for collisions between the sprite and the other group of sprites. The third argument is an odd one. It says kill the sprite, any of the sprites in the other group that it collides with. We don't want it to remove any of the walls we're colliding with, so we say don't kill them. We'll come back to that. It actually is useful, but not in this case. So that's what that false is for, but we'll come back to that. This is going to check our sprite against all of those walls and return to us the sprites. I've called them cell here, but anyway. Return to us the wall sprites that we've collided with. If we get any result, we're going to resolve the collision by simply reverting the player position to the position it had before we moved it. Okay, so we've taken a copy of the player position before we do all the updates, and then if there's a collision after the update, we revert the position back. So that's why you'll see in that code, the player will kind of stop some random distance away from the wall. Hopefully you'll notice that. We can improve that though by handling that random distance that the player moves, the player stops away from the wall, by using what's called conforming collisions. So if you run 12, the player should stop right up against the walls now. So what we've done here is we've modified the collision detection, the response to the collision, the detected collisions. We've modified the response to that to actually determine which side of the player collided with the wall that we've collided with. It's a little bit convoluted to figure out exactly which side was collided, because we actually have to say, well, if the left side was away from the wall and now it's inside the wall, then it was the left side that collided. And we do that for each side. And then if we do collide on a particular side, we can take that side of the player and move it right up against the wall by simply assigning, for example, if it's the right-hand side of the player, we move the right-hand side of the player right up against the left-hand side of the wall. And that's the nice thing about these rect objects that we've got in pygame, is that you can access all those different sides as attributes. There's a bunch of other attributes in there, like center, which returns the coordinates of the center of the rect. Yeah?
So right and left of the X positions on the grid of the sides of the sprite?
That's correct, yep. Yeah, the left and right are the X positions of the left and the right side of our rect. Okay. And this code is actually this response code will get extended a little bit later on with some other cool things. But one of the things you might notice when you run that is you can't slide along the wall sometimes. Sometimes you'll get stuck. Particularly if you hold the key that's pushing you against the wall, you won't be able to slide along the wall. Sometimes. We'll come back to that.
Oh, wow, I managed to slide it inside the wall.
Inside the wall.
Yeah, it's like, wow. Now it's like,
That's not supposed to happen. Yeah, turn no clip off, thanks. Okay, so that's all very good. Let's introduce gravity, because gravity always improves games. I invite you to now run 13. Now the controls have changed slightly here. Instead of being able to press up and down, because that would be cheating, you have to press space to alter your Y position. Okay, so now we'll be able to jump around like a loon. No, you can't just hit up to move any. Yeah. Now you'll probably notice this collision artifact. If you jump against the wall, you'll probably get stuck halfway up the wall or something. Yeah. Okay. Excellent. And you won't be able to jump off the wall. Okay. You should notice that as well, because this game, no wall jumping. All right. So adding gravity is actually pretty easy. There's a couple of things we have to keep track of to involve gravity in this, and for that matter, the jumping as well. So we're adding a couple of player attributes. We've got the player's speed. I've got these around the wrong way. We've got the player's speed in the Y direction called dy, delta y, the speed, the change in Y direction. And we've also got a flag called resting, and the resting flag tells us whether or not the player is actually sitting on a surface, and we'll use that for being able to tell whether or not they're allowed to jump. Okay, so we're going to get rid of our up and down keys, and we're going to introduce space as our jump key. And we use our resting flag to say if the player is currently resting on a surface and they hit the Y key, the space key, then we introduce an impulse in the Y direction of minus 500. Again, Y increases down, so minus 500 makes them jump up. Yay. And that's our vertical speed of 500 pixels per second. The next line is gravity. Gravity is minus 40 pixels. Hang on. What have we got here? Yeah, minus 40 pixels per second per update. Or plus 40. Yeah, the coordinate system breaks my head. Anyway, 40 down per update. I don't actually use the DT value there. I should multiply that by DT so that we're actually getting the 40 pixels per second update, but I forgot to add it in there. It would have to actually be like more than 40 then. Doesn't matter. We limit the vertical speed to 400 pixels per second. Just you've got to pick a sane maximum there, because if you don't limit that speed, it may get to a point where it starts breaking your vertical collision detection and the player can pass straight through blocks. And then we automatically update the player's Y position based on their current vertical speed. Okay, so now the resting flag, we have to manage that. So inside our collision response code, we're going to set the resting flag if the player has collided with the top of a wall object. We also clear the vertical speed if they collide with anything down or up. And the reason for that will be demonstrated later. Right, any problems with that? We're all good? Yep, resting flags, excellent. Okay, so now we're going to try and make our game world a little bit more interesting. We're going to do that by replacing that for loop, creating a bounding box around our game world. We're going to replace that with an actual map of tiles. You can create maps of tiles in your program using just text with characters in the text to indicate where walls are and things like that. That's really tedious, especially if the level is quite big. So we're going to use a tool to create our world map. And the tool that we're going to use is called, I use this tool called Tiled, and it creates world maps in a common format called TMX. And there's tons of tools out there to work with TMX files. And we're going to use a library to handle the TMX file that we're using. Because we're not crazy, we're not going to write tile map handling code today. The tile mapping format's quite simple. It's just that it would take us an hour to write the tile map loader. So we're going to have these tile maps in our game. Tile maps are basically, they look like that. That's a blank tile map. Tile maps are made up of cells. Okay, so each of those squares, or rectangles in this aspect ratio, they're called cells. Each cell inside our tile map is 32 pixels by 32 pixels, and cells, obviously, they can be empty, or they can be filled with tiles. Here we've got two tiles. Here. Go the colour. All right, anyway, so you can see we've got two different tiles there. We've got a rectangular tile and a triangular tile. And we've used them repeatedly to make an interesting shape, or semi-interesting shape. Okay, so the tile map has cells in it, and the cells can have tiles. And the tiles come from a tile set. Okay, so the square and the square and the triangle are images in a tile set. Tile sets are just collections of images that can be placed around tile maps in the cells. Okay, are we all cool with that? Tile maps, cells, tiles. Okay, so tiled is really neat. You get it from mapeditor.org, or you may have downloaded it before the tutorial because it was in the instructions. Tiled looks like this, on OS 10 at least. It has a... Right. So it has a tile map window, the actual map window that you're editing, which has the tiles that you've placed. You have a palette of tiles down the side here, which comes from your tile sets, and you can have multiple tile sets. Excuse me. And so that tile map, when it's rendered inside a game, will look something like that, where some cells have tiles assigned to them, some don't. The full tile map looks something like that. So it's a 50 by 50 cell map. And obviously in the actual game, we're just looking at one corner of the tile map. And we call that part of the tile map that's displayed, we call that a viewport. Because it's kind of the player's view on the actual map of the world that they're seeing. Our tile map actually also has layers. And so this goes back to the scene composition that I was talking about before. So you can have different layers that can be drawn in different orders to construct your scene. They can also have invisible layers. And our tile map has an invisible layer called a trigger layer. And it looks something like that. Excuse me. So the trigger layer contains information for our game's mechanics. Okay, it's not visible to the player, but it tells us things like, these are things that the player can't go through. Okay, these are things that block the player's movement. They're called blockers. The P tells us where to put the player when we start the game. That's the player spawn point. And our triggers can be all sorts of different things. We'll be introducing a bunch of other triggers as we go on. The triggers in tiled, the triggers are managed as properties. So when you get in tiled, you can like bring up a menu on the tile set, the tiles in the tile set, and you can edit properties on the individual tiles. And so here I've set the property called player. And that indicates, and in my program, I can search for all of the tiles, all the cells that have tiles which have the property player. And that's such a common operation that the TMX library actually has a function to find all of the cells that have that property set or have some other property set. Okay, so to make use of all of this, we import the TMX library, which again, I wrote this for the tutorial, so it's out there, it's public domain, do what you will with it. We're going to tear out all of the stuff that we'd written to manually construct our world. It's gone, because we're going to rewrite the way that the scene is constructed. Not drastically, but we need to use this library now. So where previously we had this loop to construct the walls, we're going to load our map of walls from our tile map. Okay, so tmx.load loads up our world from that map file. We tell TMX, when we load the map, we tell TMX what our viewport size is, so that TMX can then know what size to render the world at. Because the viewport can move around the world, we have to manage the drawing of the sprites in that world as well. The sprites are obviously going to have to move when the viewport moves. Fortunately, TMX, the tile map, can actually manage that for us as well. We just have to use we have to tell the tile map about our sprites so that it can manage the scrolling of all of the sprites that we're drawing as well. So we use a sprite layer, where previously we just used a sprite group. We're going to use a sprite layer in the tile map to place all of our sprites that need to be drawn along with the map. Is everyone okay with that? The idea of that we've got this viewport moving around, and we're telling the tile map, which is managing that viewport, that it needs to also draw these other sprites along with the tile map. And here, the next line, we're actually finding the player spawn. The find method finds all of the things that are marked with the property player. So it returns a list, and we just want the first one. So that tells us where the starting point for the player is. And then when we create the player, where previously we'd hard-coded the starting position, we're now saying start at this particular cell. And the px and py attributes of the cell tell us the pixel coordinates of the cell. The cells also have kind of an index coordinate as well. They have an x and y, which is the index inside the cell inside the tile map, which is 50 by 50. So they would have they have both that index in the map and their pixel position. Oh, sorry, yes. So our map has two layers. It has one called map, which is the visible thing that's drawn on the screen, and then it has triggers, which is that other layer, which looks like that, which is the triggers layer. Okay, so then some other small updates where previously we were calling update on our sprites group, we're now calling update on the tile map. It's the same basic API as the pygame sprite groups. And where we were calling draw in our sprites group, we're now calling draw on our tile map. So a small change to our player, where previously we'd hard-coded the starting position, we are now taking a starting location as one of our arguments, so that we're starting in the right spot. And one more change, well, two more changes. Inside the player update, we're now colliding the player with the tile map instead of the walls sprite group. So the tile map can do collisions based on properties. So we're colliding the player's new position with all of the cells that have the property blocker set or blockers set. And that returns us all of the cells in the tile map which are blockers that the player is colliding with. And the last thing is that we have to tell the tile map where to focus the viewport onto the game world. And we use set focus, focusing on the player's position. The tile library is smart enough to say that if the player is right down in the bottom left-hand corner of the map, don't display stuff outside the map. It anchors things, or it prevents the cells, non-existent cells outside the map from just being displayed. If that made any sense whatsoever. All right, so are we all okay with this? I mean, that's a lot of stuff that we've just added because we're using this new library.
But it
Good.
seems like at this point now, we can create a separation of duties in our game, right? Like our code now is, this is the back-end code, and then we can have a designer or somebody else come in, use the comment or whatever. You go ahead and do your thing, and I'll go ahead and do my thing.
That is precisely right, yes. You can have somebody else who's actually creating assets for your game, the levels, and you just have to code maybe a few new triggers, but otherwise, and they can go off and they can create the artwork for the tiles and all that stuff quite independent. Yeah. Yeah.
Sorry, where is blockers defined?
Blockers is the blockers there, that's saying to look for cells that have that property defined on them. So where previously we had, that's in the triggers layer, yeah. Okay. So hopefully you've all run 14 at this point, yeah. And so you've got an actual level to jump around in. Right, yeah.
When I try to use that tile editor, it's complaining to me about a missing rules.txt. Does that mean anything to you?
Does it actually stop it from working?
It'll complain like 4 or 5 times and then quit, yeah. Like if I try to add...
Try just do it like create an empty rules.txt or something. Yeah. Yeah, if tiled complains about a missing rules.txt, try just creating an empty one. And that might shut it up. I'm not sure what's going on there. Yeah.
Kind of a funny bug where the dude can't walk past the tile left or right.
Yeah. So I was going to bring that up.
Okay.
Yeah. So where previously we'd noticed that when the player, when we introduced gravity, you could jump up and you get stuck on the wall. Now you'll notice that there'll be other situations where you'll get stuck against things. You can't move past certain cells or something. That's because of our very, very naive collision response code. Or, collision detection and response code. So what we need to do is, it's because we've defined all of our potential blockers as just being squares. So what we're going to do is we're going to handle that. Also, you can't jump up onto platforms. You should be able to jump up onto platforms from underneath. That's a useful thing to be able to do in platforming games. Sometimes, assuming that's the sort of, I like that sort of behaviour in platform games. Sometimes you don't want that, but you know, it's good to be able to do. Okay, so the reason it's broken at the moment is because we have the cells being defined as just basic blocks. Okay, so we have this player colliding with this cell, just resting on the top of it, and when we move to the right, we allow them to slide across the top of that cell, because we've already solved the problem of making the collision hit, you know, the edges. But once they hit the boundary between that cell and the next cell, they're colliding with the left-hand side of the next cell. Because, again, we've just defined the blocking here as being just a solid box. So what we need to do is actually define the actual boundaries of the cells that should be collided with. So we're going to modify our blockers in our map to just be the sides that we want the collisions to be handled on. And so instead of that basic square blocker trigger that we had before, we've now got explicit side blocker triggers. And in this way we can avoid any unwanted collisions as well. So you can see that the platforms here only collide on the top. So if the player comes from underneath, it can actually pass straight through those platforms to be able to land on top. And we've actually defined a full set of blockers in the triggers tile set. So it doesn't matter what shape of thing that you've got in the map, you can define the correct sides that you want the player to collide with. So if you wanted to, you could actually have those platforms be solid by using the blocker that has the top and the bottom set on it. And obviously for the ends you'd have the cap as well. So this makes our collision response code a little bit more tricky, detection and response code. So now we actually have to add into our detection code a check to see whether or not the blocker that we've collided with actually has the side that we're checking against set. So in the blockers property on those tiles, we've actually defined 1 to 4 characters, LRTB for left, right, top, bottom, to indicate whether that particular blocker trigger is solid on that side. And so now we only collide with the sides if the blocker indicates I'm actually solid on that side. We cool with that? Yep. So now, running that 15, you should be able to run along and jump up against the wall and slide down it and do all sorts of stuff and jump up onto the platforms and all that fun stuff. And hopefully not jump through the world into the...
No, you can. I did it.
No, don't say that.
But it was only the second time.
All right, well, I disavow any bugs. Sorry? Okay, so left, right, top, bottom. Yeah.
You can reproduce, just press the left-hand arrow and you'll probably reproduce it on your system.
Nope, I refuse to acknowledge any bugs in this code. We can look into it later. Okay, brilliant. All right, so our player is now jumping around like a loon. We've got a nice level that we can jump around in. It's all cool. It's still a bit boring. Let's have some enemies. Yeah. Okay. So if we have enemies, we have to answer a few basic questions. Where are they in the level? And if they move, how do they move around? And do they do anything else? Like, do they shoot? the player or shoot back, or do they jump, or do they, create gas clouds or something? I don't know. Maybe they alter the level when they pass things. Who knows? So in terms of the first two questions, we're going to implement a very, very simple enemy behaviour, very common in platformers, where the enemies start in one position and they move until they hit a certain trigger, and then they change direction and they move back again. In terms of the trigger layer, we've altered it now to look something like this. So we've got little E triggers to say, create an enemy here, and then we've got little reverser triggers to say, when the enemy hits this reverse trigger, change the direction to go the other way. Really, really simple stuff.
Did you guys create this tile set?
Yeah, I created this. This is simple. Yeah. I threw this.
Tile set though, is that where you name the triggers and say like this is a blocker, this is a...
Yeah, in the actual tile set, there'll be a property in there saying reverse or enemy. Yeah. Yeah. It's important that you have to, when you add the tile set to your tile map, when you add the image to your tile set, you have to set the property on the tile to say what is special about it, because the image doesn't tell it that. It's the actual property that tells it that it's special. Yes. Right. So enemy triggers, this is a platform game obviously, but enemy triggers can be used in all sorts of different ways. So let's talk for a moment about a side-scrolling shoot-'em-up game, okay? So here we've got a game world, and we've got a viewport, that's the red thing, and we've got the player, which is the... I threw this together in like 2 seconds. Sorry about this. Okay, so the viewport is going to scroll, okay? As the game progresses, the viewport scrolls along the playing field as the player is moving. At a constant speed, that's how these side-scrolling shooters or vertical scrolling shooters or whatever, that's how they work. Okay, so the player is moving along. Moving along. What we're going to do is, the way that most of these games work is that they'll have a trigger layer so that they're, and it has enemy triggers in it. So we'll whack an enemy trigger in here, and when the enemy trigger is exposed by the viewport, we create an enemy. Okay? Like that. That's an enemy. Yeah, you can tell because it's red. Don't kid. There's a guy who, I run a video game programming challenge called PyWeek, right? I've been running it for like 7 years or something crazy like that. It runs twice a year. There's a guy who's gone into it at least half of them, probably more than half of those times. And every single time he's created a game using pygame draw commands, and he's called his games a block game 1, a block game 2, okay? And he just does, very, very basic graphics like this. But he does some interesting things with, the mechanics. Some of them not particularly interesting, but some of them interesting, And he just mucks around. He's not relying on his art skills. Anyway, so our enemy trigger has been exposed by the viewport. We create the enemy, and then we can pew pew at the enemy. Okay, so that's how side scrollers work. The viewport exposes triggers as it moves along, and things happen. The same trigger mechanism could be used to play sound effects, to start music playing or stop music playing. It's basically a sequencer that's running. Okay, so that's side scrollers. There's a side scroller in the directory there that you can have a poke at if you'd like to, which implements that. But for now, let's look at enemies. Okay, so to implement enemies in our game, we're going to have to create a whole new class for them because they've got their own specialised behaviour. They look kind of like the player to start off with. I mean, they're a sprite. They've got an image and a position on screen. They've got a starting location which is going to be passed in when the enemy is created. The important thing with the enemy is that they've got a movement direction. We have to keep track of which direction they're moving in. 1 means they're moving right. -1 means they're moving left. The updating for these enemies is dead simple. We move them in the direction they're moving in at a constant speed of 100 pixels per second. We then run a collision check against the triggers map to see whether or not the enemy has run into any of the reverse triggers. And if they have, we change their direction. We also conform the movement, the position to the trigger, because if we don't do that, we can get some collision error and maybe collide with it twice, or it could just get a bit confusing. So we actually move the thing right up against it so that when it starts off again, it's nice and neat. And then we see if the enemy has collided with the player. And if the player is touching an enemy, it's game over. Okay, so we set the is dead flag on the player.
Can you go over the netcode? I'm
Yeah?
not understanding the passing of groups into...
Oh, okay, sorry. Okay, groups is a standard argument to pygame sprites. And it basically says, add this sprite to any of the groups that are passed in. They're optional, but sprites have to belong to a group for them to appear on screen and to be updated. So it's convenient to be able to pass in those groups, or maybe just one group in this case, when the sprite is created. Okay, and so the pygame sprite base class handles all that. That's why we call the base class as the first thing. We pass it in the groups, and the sprite will be added to those groups. You'll see in a moment, in fact on the next slide. I'll move on to the next slide. So you can see here where we create the enemy. The second argument is the enemy's sprite group, or it's actually a tile layer, which is effectively a sprite group. So the enemy will be added to that layer automatically for us. So yeah, we find all of the enemy triggers in the trigger map, and we add enemies to the game at all of those locations. In a platforming game, unlike the side-scrolling game, where you add them when they're exposed by the viewport, in the platforming game, we just add them all at the start, because there's not going to be that many. And you know, even if there is tons of them, a lot of them will be off screen. It doesn't really matter. They're not going to cost us a lot to update, even if they're not on screen. And so, yeah, we just create them at the start when the level is loaded. And so we've also added those to a separate layer so that we can access just the enemies later on, which will come in handy. And obviously we need to keep track of the player's health so that we can check that later on to detect when they die. Okay, so if you run 16, you'll be able to jump into enemies and die. Very exciting. When do I run out of time, by the way? Anyone know when I'm supposed to stop? Sorry? 12:20. Excellent. All right. Okay, so we're going to take a little diversion now, and we're going to play with a little bit of basic animation, really basic animation. So our player at the moment has been just, up until now, has just been a single solitary stick figure picture. What we're going to do is we're going to alter the image of the player, very, very basic animation, alter the image of the player to indicate which direction the player is pointing in. So if you run 17, you'll see that, you know, the image updates. This is really, really easy to do. We have to load our two images. So where previously we were just loading the single player image, we're going to load a left image and a right image. We're going to set the image, the first image being displayed to just one of those, because it doesn't really matter which one, as long as it's consistent with the direction they're facing. And now we're going to have to keep track of which direction the player is pointing. Actually, we don't need it for this, but we're going to do it anyway. We're going to keep track of which direction the player is facing. And then when the player hits the left or the right key, we just swap the image on the sprite out to be the appropriate image, the left or the right image. You could extend this quite easily to actually include an animation of the player walking by adding in some simple checks for timing checks. So you could say, after half a second, or less than half a second most likely, change the image to one of the next in the walking animation images. I'll talk about image animation. Actually, next slide. So you can swap this image out with anything to represent what's going on with the player. You could have a player dead image, which is put up there when the player dies. Whatever's appropriate. It's just a case of swapping the image. You don't have to do anything else. Just the next time the sprite is drawn, it'll use the new image. Okay, so image animation, we've already done, position on the screen. When we can change what the image is that's being drawn for the player over time as well. Here's some basic image, some basic animation frames for walking and various other movements. This is from a classic book called How to Animate by Preston Blair. It's used in cartoon animation courses. It's like pretty much any cartoon animation course will use this book. And there's samples like this and countless others out there on the interwebs for drawing things like walking cycles and running cycles. And you can basically whack that into your image editor and trace over it in the style of your character, and there you have a walking cycle. It was obviously a very cartoonish style, but it's a great starting point. Here's some animation images that I created for a game a few years ago. Actually, it's the one that had the scenery that you saw before. It's pretty crappy, but it did the job. It was actually, I used the source. The source that I used was actually, I took a short video of my daughter walking, and I used that as and then I completely screwed it up because I missed a whole bunch of the key movements. I mean, you compare this to, you compare that to the amount of movement in the basic walking there, it's quite different. But it worked. I mean, the character looked like it was walking. And so all you have to do is, keep track of time and say if enough time has passed, switch to the next image in the walk cycle. And if enough time has passed, switch to the next image in the walk cycle. It's really easy. You have an array of images and you use the next one, and when you hit the end, you go back to the start. A little hint though, make it life easier for yourself. Make each of the frames of the animation the same size. You might have to modify your artwork a little bit to do that, but it'll be a lot easier if your frames are all the same size. Okay. Another sort of image animation is an explosion. So this is 16 frames of something blowing up. And again, you just take the images in an array and you play them through, and this one, when you hit the end, you stop, you get rid of the sprite. There's a program that generates these images. I unfortunately couldn't remember what it was, or I'd give you a reference. But yeah, it generates explosion frame sets. It's really, having said that though, it's really easy to draw this. There's a bunch of tools out there for drawing pixel images like this, animations like this, where you can construct them from, you start off with the end one and you just keep on adding bits to each of the new frames, and yeah, it's really easy. Okay, so that's animations. Let's do some shooting. If you run 18, your little dude will now have the ability to make bullets. Shift, the left shift key is the shoot key. All right, so there's a few things we have to look after if we're going to make bullets in a game. We have to know where they start. There's actually a couple of considerations there. We have to know how long the bullet's going to live for, because we don't want the bullet to go on forever and ever and ever if it doesn't hit something. And we have to limit the rate that the player can shoot. And we call that the gun cooldown. You know, the amount of time before the player's gun can shoot again. For the positioning in our game, we're going to go with a very basic approach of saying just the mid-left or the mid-right of the player's sprite. And fortunately, the rect implementation actually gives us that coordinate. It's called mid-left and mid-right. So we can just say, if the player is facing right, then we just start the bullet off at the mid-right. So we're going to whack in a new class for our bullets. And bullets are even dumber than enemies, obviously. They have a direction which is fixed when they're created. They're created at a specific location, and they have a lifespan. These bullets are going to live for 1 second. The update, obviously a lot simpler than the enemies because they just move in a single direction. They don't reverse or anything like that, and they move until their life runs out. Once the lifespan has been decremented down below 0, we kill the bullet. Pygame sprites have this really handy function, kill, a method called kill, and kill removes the sprite from any groups that the sprite belongs to. So it just doesn't appear on screen anymore, and more likely than not, you won't have any other handle on the sprite, so the sprite will be garbage collected and you won't see it ever again. So sprite.kill removes the sprite from display. And as I say, we move the sprite in a constant 400 pixels per second in whatever direction it started moving in. And then we collide the sprite with any of the game enemies. And here you can see we're now using this true flag so that if there is a collision with any of the enemies, the enemy that it's collided with will be removed from the game as well. The kill will be called on that enemy that's collided. So that's what that true flag does at the end there. It doesn't call kill on the sprite that was passed in though, so we actually still have to call kill on the bullet to remove it from play as well. If we don't do that, the bullet will keep going and possibly run into other enemies.
Can you override kill? So that, for example, you're doing the sprite collide where it's going to kill the enemy, and you want to put an explosion there.
Oh,
Do you have to implement the explosion first and then have it kill it, or is that something that you can do with your enemy class?
what you would probably do there is you would have another class, which is your explosion class. Okay, so it's a very, very basic sprite that just has an image set that's going to be cycled through and then it kills itself. And you would just spawn one of those in that if statement there. You'd spawn a new explosion sprite class at that position and it would just run. You can add that to the game sprites group, which you have a handle on. The game has a sprites group that you can add it to. And that sprite will then get its regular updates so that you can animate it, and its animation will run and it kills itself, and it's all self-contained. So you've got a single line that's called here to create that effect. Yeah.
Just so I understand, that when you pass the true argument to sprite collide, that will automatically call kill, sprite.kill on any of the sprites that it's collided with.
Yeah.
And that kill will just remove them from the group immediately.
Yeah,
Is that what it does?
that's what it does. Yeah.
If you didn't spawn the explosion, like you're talking about, both the bullet and the enemy would just disappear.
That's correct. So yes, the true flag says any of the sprites in the game enemies group will be removed from that group if they are, and any other group they might belong to, if they are collided with, and that will remove them from display. So they will just disappear. And you could play an explosion animation at that point if you wanted to. Yeah.
I just want to be clear, is there any reason you wouldn't want to override kill, or is it just a
Again, you wouldn't necessarily override kill. Kill you leave alone. Kill you use to just remove the sprite from display. You might add in some other things here to do some other stuff. So to create a new explosion effect.
So that's why you're calling self.kill again inside of...
So the true flag says kill any of the enemy sprites
that are collided with. It doesn't kill the sprite that we're colliding with those enemies. So to kill that sprite as well, we have to actually explicitly kill it if there's a collision.
Is there any kind of hook that you can run on kill? That you could use to...
You could override kill if you wanted to by just simply subclassing, adding it to your class. So the enemy's class, you could write a kill function on that. But there might be other reasons why enemies are removed from the game other than being exploded. So you'd probably want to add an explicit explosion here and maybe a blood splatter choppy thing, so something else that kills them. Are we all good with that? Yeah, I hope that answered the questions there. Okay, so we add another attribute to our player to manage the gun cooldown, the rate at which they can shoot. We set that to 0 initially so they can shoot. And then inside our player update, which, as I said before, it's starting to get longer and longer as we add more things to the player, to what the player can do. We add in the handling of the shoot key, which is by default here, well, as I've defined here, the shift key. And so if the player hits the shift key and the gun isn't cooling down, so if the gun cooldown has any value on it, then we can't shoot. But if it's 0, then we'll be able to shoot. And depending on which direction the player is facing, we create a new bullet. And we add the bullet just to the game sprites group. Doesn't have to belong to any particular group. So the top level game sprites group will do. And we set the cooldown to 1 second. You might set that to half a second if you want the player to shoot more frequently, or 0.1 of a second if you want them just to go bleh. And then we cool the gun down by just decrementing it by the amount of time that's passed, limiting it to 0. If it's hit 0, then we keep it at 0, and then the player can shoot again. All cool? Yeah, a bit of contemplation there. Yeah.
I was kind of curious about something else. If the bullet, let's imagine for a minute you were running on a fairly slow machine, or the bullets were really fast. How do you deal with the possibility of the bullet being on one side of the enemy in one update, the other side on the other update, and not having collided?
Okay, all right. So the question is, how do you handle the situation where the bullet is moving so fast that it might, in one update, travel from one side of an enemy to another side of the enemy without actually colliding with the enemy with the simple collision detection that we're doing? The answer is that you end up having to draw, you do a different collision detection mechanism where for bullets it's actually quite easy because bullets are typically very small, so you can just say, well, there's a single pixel, and you draw a line from the start position to the end position, and then you collide the line with any of the enemy rectangles. If you're talking about shapes more complex than just a pixel, then you're talking about maybe colliding a circle, which has been, I'm trying to remember the word, but there are methods for colliding a circle which has been extrapolated over some distance, representing the amount of distance it's moved in one update, and colliding that with a bunch of other stuff.
So the basic idea is you take these 2 points and you construct a shape that covers the space between, and then intersect that shape.
Yes. You sorry. What you said. So I was going to try and repeat that for the camera, but yes, you have to extrapolate the position, so you draw a shape from the start position to the end position that represents the rough shape of the thing that's being moved for that update, and then collide that entire shape with everything in the game world. And again, that sort of thing, there's plenty of stuff out there for doing that sort of stuff. My suggestion is just don't move stuff that quickly. Okay. So, we're shooting. So we've got a basic game now. You may notice that you can't win. I didn't add a winning condition. That's an exercise for the reader. It should be relatively obvious how that sort of thing can be done. If it's not, feel free to ask later. Okay, so let's add some sound effects. Yeah. Okay. Sound effects in Pygame are actually really, in most game engines for that matter, are actually really, really easy. You kind of, when you start the game up or start a level up, you load a bunch of sound effects off disk. They might be WAV files or MP3s or OGG Vorbis files. And that gives you a sound object, and then you can typically just invoke play on the sound object, and that'll play it. There's more complex mechanisms available to you if you really need them for managing, playing multiple sound files and stopping them and starting them and things like that. But the basics are pretty simple. Load a sound object and play it. And the same thing can be done with background music. When the level starts up, you load a background music file and you play it. And then when the level stops, you hit stop. So if you play 19, the room will start filling with sound effects. Somebody got an enemy. Excellent. Okay. The one thing you have to watch out for is if you're playing a lot of sound effects, you might overload the sound mixer. Most sound mixers can cope with about 8 or maybe 12 sounds being played simultaneously. You want to try and keep a limit on that. So loading sounds is easy. We load them up off disk with the mixer sound object. And that gives us an object back which we can then call play on. So explosion.play or shoot.play, jump.play. Really easy, and that just plays the sound effect. Nice and easy. The sound effects were created with this tool, which is called CFXR. This is the Mac version of a program called SFXR, and it basically lets you just generate random sound effects in certain themes or completely random. The center bit there is actually an emulation of the old school 6502 sound chip from like Commodore 64s and stuff. Not 6502, what am I saying? The other one. Anyway, the SID, the sound chip. Good old SID. Yeah, from the old Commodore 64s and that sort of era sound generation. Right, and it's really easy to use. You kind of hit the buttons on the side there, and the interface is basically the same. It's just this one looks like Carbon because it's the Carbon version. You hit the buttons on the side there, and you hit the jump button, and it generates a jump sound effect. And you keep hitting it until you hear a sound that sounds like the one you want to use. And you get a list of the previous sounds being generated going down there, the side there. And when you've got a sound that you like, you select it and you hit export, and that gives you a WAV file, and you can load that straight into Pygame and play it. And you can also tweak things. So you can grab the slider thingies there and tweak them. And if you hit the play on change, it can be really fun. So because it plays the sound effect every time you change a value. SFX, there's actually a Flash version, I think, as well. So like you can go to a website and generate these sound effects. Okay, so our game architecture is looking pretty good. There's some things we could add to the game at this point, which I didn't add. So the player might have multiple lives, which suck. No. It's kind of traditional for platformers to have lives, but as has been pointed out previously, they're a little bit annoying and a little bit stupid. So think of a different thing that you might do if the player dies. Go back to a previous save point, whatever. It's nice to have a little bit of structure outside of the actual level that's being played to like introduce the player to the game, to give them instructions, to maybe have some options menus, have a little splash screen that's skippable, things like that. Extra stuff around the actual level that's being played. Maybe your game has a world and you have to select the level to play from a world map, that sort of thing. If you run 20, that actually introduces a simple, what we'll call scene in before the actual game plays. And it's just a basic menu with play and quit. And if you select play, it plays the game. If you select quit, it quits the game. Really, really simple. You can add more options to this, obviously. I've used a library called Kes Menu, which is available. I just found it's the first hit I got for pygame menus on the pygame website. And it's pretty easy to use. It has some sort of special effects that you can add in to animate things and stuff, and you've got a little bit of control over it. But, you know, really, really simple stuff. But the point is that I've added this extra scene with almost no effort in terms of my game architecture, where previously at the bottom of our program we had game.main. I've now invoked menu.main. And inside the menu, when the player selects the play option in the menu, we create our game and invoke that. So the menu is still there, it's just we've handed control of our program off to the game, so we're running different code now. And when that code finishes, it'll return from that main and we'll jump back into the menu. And the menu will run again until the quit is selected, or we can play again. We jump back over into our main. So this is how basic scene management is done in pygame and many other libraries. You just start running a different main loop. And it's all nicely self-contained. Okay. Yeah. All right, so some other things you might want to add. So scenes you'll definitely want to add to your game. New levels. Obviously you could add the actual map file that's being loaded. You could add that as an argument to your game class. So when the game class is created, you could run a different level. And you could actually have a trigger inside your map to say, when the player hits this trigger, load a new level. And the actual trigger inside the map file, the trigger could actually be the name of the level file to load next. We can also add special effects. Particles, every single game in existence is better with particles. Python has a really neat library called Lepton, and it works with Pygame or OpenGL. Obviously you can use those simple image animations like explosion animations or stuff, but particles rule. Add particles to every game, it'll be better. There's some example effects in the demo code, the tutorial code that you've got there. I can't remember what the file's called, but it uses Lepton. So if you install Lepton, it requires compilation, so it's a bit finicky, but you can run those, and it's just some basic animation, particle animations.
So if it's
Effects.py, thank you. Yep. If we're quite finished. Okay, so that is our basic platformer game. Now, the reason I chose the platformer game for today's game construction is that it's introduced a whole bunch of important concepts that are a bit tricky to get your head around when you start writing games. But most importantly, it's introduced that concept of tile mapping, because tile mapping is used in tons of 2D games. In fact, there's not many 2D games that don't use tile mapping. And so that's why I introduced that. And in fact, some other game types that you could probably immediately go away and start writing at this point would include Minesweeper. Minesweeper's a doddle. In fact, I imagine there's a few of you possibly that could also already be saying in your head, yeah, I know how to write that now, hopefully. Because Minesweeper is simple. It's an array of images, and you detect mouse clicks, and you change the image in the array depending on what the contents of some other array is. And if it's the wrong thing in there, then the player's game is over. There is an example of that in the tutorial code, and you'll see it's really, really simple code. This is why it came with Windows. I shouldn't have said that. This isn't being recorded, is it? So another type of game is a driving game, where a simple top-down driving game, and again, there's an example of that. The collision detection is a bit fun because to detect collisions with the map, you have to have a separate layer of the map which actually has in solid colour all of the various stuff that the player could collide with, but also the stuff that might affect the player's car in other ways, like oil slicks and things. And that stuff is specified as pixels, so that you can actually check like the four corners of the car, where the four corners of the car are, where the wheels are. You can check those to see whether or not those wheels are actually colliding with anything, and that's how you do like the collision detection in a car driving game. It's a little bit funkier. The side-scrolling shooter, that's in there as well. Tower defense, I didn't get around to finishing that one. I started coding it on the playover, but then I drank too much. So yeah, I've already said this. Minesweeper, you're detecting clicks and you're exposing contents of cells. Car driving, yep. The platform game, that's weird. That should be saying side-scroller. Whoops. And tower defense. Tower defense is actually pretty easy. You can use the TMX library to do this, or you can just have a simple array of cells, and you're placing towers with the map with the mouse. The figuring out where the creeps go, the bad guys that are basically going from start to finish, is really easy. You look at your map, starting at the exit point. You assign each of the cells that you discover starting at the exit point. You assign each cell a cost, a movement distance from the exit. So you just increment it up by one for each cell you travel away from the exit point, and you fill an array with those values until you've basically assigned every cell that's movable a value. And then so when a creep has to move, it just looks for all its neighbour cells and figure out which one has the lowest value based compared to the current value, and it moves to that cell. And it'll keep moving to the next lowest value until it gets to the exit. I mean, it's a really, really simple game. Yeah, so from here, you have the pygame docs in the material that I just gave you. If you'd like some more explanation around pygame and how to create games, there's this great website, Invent with Python. The guy who wrote that, who created this, he's written a free book called Invent Your Own Games with Python. That's targeted as a younger demographic, so early teens or maybe even just a little bit younger, intended to teach kids how to program by doing fun stuff. He's also written a second book. He's just finished up writing a second book, which is a slightly more advanced book about Pygame and writing games in Pygame. And that's at the same website. And I encourage you all to come along in about 2 months' time and play along at PyWeek, which is a game programming challenge that I run, as I mentioned before, twice a year. It's number 14 this year. My God. And the idea is you write a game almost from scratch in a week. And it's really easy to write a game. You can write a game over a weekend. I run it over a week because I have a family, and I can get in maybe a couple of hours a night, and that's enough to write a game. It doesn't have to be anything fancy. It's just write a game, and it's good fun. It's lots of fun. So I encourage you to come along and do that. The information for that obviously is on the PyWeek website. And that is all I have prepared. So I invite you to ask questions, have a play around with the code, have an experiment, break it, do whatever you want to do, and I'm here to help. Katie's here to help if you'd like to muck around. Thank you.